favorite talk by one of the 6 new postdocs that we have, Keller, who does mathematics, came from Toronto University. And next week we'll have a celebration of the beginning of the year. That would be after the colloquium. And we will start with a group photo. We will step up. Hopefully the weather will be nice. I haven't checked it, but hopefully it will be nice, and we'll take a group photo that is posted usually on the BHI website. That will be next week after the colloquium. Other than that, we already discussed the expected LIGO announcement on October 16th, so stay tuned. We have a representative here, and you can ask her questions, but it's not clear she will answer them about this event. Hi.
Yeah, so as Avi said, our first speaker today is Jordan Keller, who's one of the new BHI fellows. Jordan received his PhD from Columbia, and his specialty is to study how to adapt techniques in hyperbolic partial differential equations to understand stability and singularities in black holes. And so today he'll be telling us about linear stability in higher dimensional Schwarzschild black holes.
Okay, thanks very much for letting me speak, and thanks to the BHI for taking me on as a fellow and for keeping the lights on for me. So, talking a little bit about some work in progress with my advisor Mu-Tao Wang and former classmate of mine, Pei-Ken. So last year we did this result on the stability of Schwarzschild in sort of the standard classical 4 dimensions. And we're just interested in sort of seeing how far this result can be generalized or pushed. So, just now, I'll talk about the next 25 minutes. Let me just give some background, some context for what's going on. And then we'll talk a little bit about, so we'll introduce the Schwarzschild-Tangherlini solutions, this sort of higher dimensional generalization of Schwarzschild, and also talk about this black hole stability problem, what to expect. And then we'll talk a little bit about this sort of linearized gravity, that is to say, studying linear stability. And the main thing to sort of focus in on here is spherical symmetry. It's sort of the feature of the Schwarzschild-Tangherlini solutions that will make studying linear stability tractable. And so having talked about that in sort of a general sense, in this second point, we'll move on and we'll pivot, and eventually we'll study it in a specialized sense on the Schwarzschild-Tangherlini black holes in particular. So this is the higher dimensional generalization of Schwarzschild. I guess it was discovered by this Tangherlini fellow in the 70s. It's sort of, you think about n is equal to 2, so orbit sphere dimension 2, then you just sort of specialize down to the 4-dimensional Schwarzschild. Let's see, we've got this mass parameter m, which is positive. We've got, just keep track of, we've written it in this coordinate system tr and some spherical coordinates. Let's note that there's sort of a coordinate singularity. There seems to be a problem in the metric near this sort of horizon coordinate. This is the n minus first root of 2m.
I have a naive question. Are there physical models that suggest these, or is this suggested through the mathematics itself?
In the sense,
why are you looking at higher dimensional solutions? Is it a mathematical question, or is it something that arises in some physical models?
I would imagine that there's some application in string theory, but then I'm sticking my neck out because mathematically, it's simply an interesting generalization, I guess, to me.
Which is reason enough to look at it. I just wanted to understand where you started.
So there's, as I said, a coordinate singularity. Of course, this can be extended beyond, and we'll see the black hole region. So, as I say, these coordinates are sort of the standard Schwarzschild coordinates covering the exterior region. This boundary radius, this n minus first root of 2m, is sort of the event horizon radius. And we can think about going within it or going beyond it into some black hole region. Primarily, we're going to be working on this exterior region for this sort of domain of outer communication. So the Schwarzschild-Tangherlini solutions you might think of as sort of the simplest non-trivial solution of vacuum gravity. And generalizing sort of the vacuum Einstein equations, we're simply saying that the metric is Ricci flat. So remember that the Ricci tensor is just some sort of second partials of the standard metric. And it sort of has the appearance, you can almost think about this as like a wave equation for G for the metric. this is owing to the Lorentzian signature that we're working in. So the stability question is sort of whether and in what sense, so with what asymptotics the associated solutions, these black holes, are stable. We can think about them as sort of equilibrium solutions or some sort of stationary or static solutions of these Einstein equations, and then we might be interested in what sense they remain stable under perturbations. And I guess the best known result is not even something for black hole spacetimes. It's for these, just for standard Minkowski space in 4 dimensions. This is work of Schwarzschild-Tangherlini from the early 90s. So this is the sort of full-on nonlinear stability. In this talk, we're just going to be focused on linear stability. So the Schwarzschild-Tangherlini result really gets back to this question of in what sense these black hole solutions are stable. I mean, I guess the sort of canard in the math community is that like we need to be interested in whether these are even physically reasonable models. And maybe the fact that we have this EHT telescope taking a picture of one would suggest that they are perfectly physically reasonable. So this is not the right question to be asking. I guess the right question to be asking, or the interesting information that could come from a more refined study from the math GR community, is the second piece of in what sense are these stable?
Can I ask a general question? Can you give me some intuition as to what it means for a solution to be stable and not stable?
Yeah.
What's the physical manifestation of a stable solution versus unstable solution?
Decay to gravitational waves, for example. State can decay, disappear.
So yeah, so when we linearize, for instance, so the linear picture would sort of be gravitational waves, and you could be interested in, for instance, what are the asymptotics, what are the fall-off rates for observers sitting in null infinity? So when we're observing these gravitational waves, how quickly are they dispersing? The earlier sort of physics community approach was to study sort of quasi-normal modes and sort of mode solutions in general, which assume exponential fall-off. But actually, you can get a much more refined and sort of careful understanding of the asymptotics at null infinity if you were to study it maybe in this more careful way. Does that give some sense?
A little.
It could also be that it just blows up spectacularly, in which case well, it would be not so good for us either.
Okay.
For the Schwarzschild-Tangherlini story, would you, if you want to prove stability for small perturbations with compact support in some spatial region, is that a trivial problem?
No, I don't think so.
Because the problem is that you can take things which are very widely separated, you can aim them at a point, and then they make a black hole.
I see, so
Right. So Schwarzschild-Tangherlini have this very complicated norm that rules out that possibility. But if you're just in a compact region, I'm just wondering, that is the reason it's so hard to prove stability of Minkowski space, right? Because you can have a big ring of stuff that's focused at the origin, arbitrarily small, and then you make a black hole. But if you're trying to prove the stability of a black hole, I'm not understanding physically why it should be hard. Is there an analog of that kind of phenomena that you would be worried about?
That you're worried about? Yeah, so you're worried about, I actually don't know, I mean, somehow you're imposing asymptotics to rule, in this Minkowskian setting, to rule out the formation of black holes. That's what you're saying. This is the crux of it. That's what the crux of their argument is.
Yeah.
Yeah.
And they had to do it in a very...
I think it's more just the case that we sort of know that Keller, for instance, sort of should classify these stationary solutions, and we want things to settle down to equilibrium states. So we sort of want to impose data in such a way that the thing ultimately settles down to Keller. I don't know if it's so much we're worried that it'll form some new physical phenomenon that's so dangerous, or so bizarre, so different from what's already there, from the black hole that's already there. So I guess it's maybe less satisfying than the Schwarzschild-Tangherlini type of result. So anyway, the asymptotics that Schwarzschild-Tangherlini give at null infinity led to all sorts of interesting things. In particular, Christodoulou, as a consequence, had this sort of nonlinear memory effect, which it turned out was a comparable magnitude to the sort of linear memory effect that physicists knew about 20 years prior. That's sort of something interesting that maybe in a LIGO or something like this could be detected. Moreover, Laura Dunay, this other postdoc, was showing me this from your paper with Hawking and Perry about these conserved charges. It seems like it relies in a very serious way upon the asymptotics that Christopher Kleinerman derived. On the other hand, those asymptotics are really only true for things that are sort of resembling Minkowski. It would be nice to sort of extend them to settings where you have a black hole in the deep interior. So in that sense, I guess that's maybe a more specialized type of comment, but it would be helpful to extend this sort of result from flat space to settings with black holes involved.
Wait, the asymptotics don't care if there's a Minkowski, if there's a black hole in the deep interior.
But we don't know. I mean, we don't know if Schwarzschild were a care. If the black hole were already present, we would give the same asymptotics, I guess is the point. I mean, hopefully the asymptotics should be the same, but we don't actually know that in a rigorous sense. So the physics literature primarily studied this problem by looking at solutions with extreme, fairly simple time independence. They looked at these sort of mode solutions where we're interested in e to the I omega t time dependence, omega being some sort of complex parameter. And so in particular, we're worried about, or we're interested in ruling out sort of exponentially growing modes where this omega, this complex number, has negative imaginary part. So this is the sense in which physicists try to rule out stability. It was in the sense of something growing exponentially without, and doing all sorts of nasty things as time evolves forward. But actually, you sort of need to take a more refined approach, especially if you want to, again, get these sort of refined asymptotics in null infinity. So these techniques were developed, I guess, first by Kleinerman in the 80s and applied to Minkowski in a very successful way. And I guess in the past 10 years, the community has developed or sort of transplanted these methods into the study of black hole spacetime. So now it's sort of possible to move beyond just studying mode solutions. So the basic research program is, first you sort of fix the black hole background and study waves propagating on the exterior region. Next you study linear stability, which is sort of where we're at in this talk today. And then finally you would move on to some sort of nonlinear statement, which would hopefully, again, for application purposes, give you some sort of refined understanding of null infinity.
What do you mean by scalar waves? Do you mean scalar field or?
Scalar field, yeah.
So you put an extra component.
Yeah, but you don't think about it as being coupled with you just think about the background as being fixed, so some fixed geometry, you put this field on it and see how it evolves. So you should expect it to disperse. That would be the hope.
Okay, but you're assuming the existence of the field, which might not be the
Yeah, so it doesn't have really any sort of physical picture. It's just that when you study the linear problem or the nonlinear problem, you sort of end up with wave equations for quantities which are of physical interest. So studying first the scalar wave, which is just this fake thing, helps you later on. You sort of discover the essential techniques that you'll need later on. Okay, so yeah, I should say that the decay of scalar waves, this project has basically been completed in the last 5 years. So Schwarzschild was done by, I would say, a number of people, but Fermos and Rodniansky especially, maybe in 08 or 09. Keller was done about 3 years ago by Fermos, Rodniansky, and Schwarzschild-Tangherlini. And linear stability of Schwarzschild is sort of where we are, at least in this sort of classical four-dimensional setting. So nothing. Kleinerman apparently has some work in progress on nonlinear stability, and it's sort of forthcoming. This is for Schwarzschild. So let me try to unpack the linear stability, the sort of second point. So if we think about linearizing the Ricci tensor operator about a particular Schwarzschild-Tangherlini solution, so now we're studying sort of a metric perturbation or gravitational wave, this delta G. So think about it as sort of a two tensor on this fixed background. And now it's satisfying some set of equations. This is just some very, very complicated system of linear partial differential equations of second order. And you can sort of think about this delta reach as being like box. It's like the D'Alembert-ian, so this is like a wave equation for delta G, this metric perturbation. So there's a couple of issues beyond just saying, so again, the picture would be that this is just a box of delta G is equal to 0, so it's like a wave equation. So again, we would expect dispersion in line with this decay of scalar waves. This first point, we would sort of use these techniques to understand dispersion. There's a couple obstacles. First, that we have diffeomorphism and variance of the underlying equations, and so we should have pure gauge solutions. So given a covector field X, taking the lead derivative of the underlying space-time metric, I should always just create some sort of fake solution corresponding to an infinitesimal change of coordinates.
So I have a question. So you said the physicists do this mode analysis. That is a linear problem, right? It's a linearized version of the problem. how is what you are talking here different from what t to the I omega t analysis?
So we're both studying linearized versions of the
Yes.
problem, but we're studying a linearized version with allowing the full range of dynamics. So I mean, they're not just studying a linearized problem; they're also studying. I mean, they're also studying particular. They're assuming particular dynamics. I mean, dynamics of the form e to the I omega t.
You're saying that's not a complete set.
No. In fact, I mean,
Okay.
so they would find decay that in that case it's exponential, but in fact the decay is much weaker than that. Decay is much more like 1/t.
And you can't do that by just summing up a whole lot of
No,
exponentials.
so you could do, for instance, using like the spherical symmetry, you could use like spherical harmonics and sum these things up, but the sort of Fourier transform type of thing, like doing some inversion of this process or some superposition of these modes,
Yeah.
to my knowledge, this has not been accomplished in these asymptotically flat settings.
I see.
It would be strange. I mean, all these things would be exponentially decaying, but in the end, I mean, the best you could really expect is something that's decaying like 1/t. It's a little bit, much weaker. Is that okay? Okay. So some obstacles are we have this diffeomorphism variance, these pure gauge solutions that I just mentioned. So infinitesimal change in coordinates, and moreover, these are sitting in some larger family, sort of generalizing care to these higher dimensional settings. This Myers-Perry family, which have sort of mass as the Schwarzschild does, and also these angular momentum parameters increasing with increasing dimension. And so we should expect to be able to deform from Schwarzschild-Tangherlini to Myers-Perry, in which case we need to sort of mod out. So we sort of need to mod out by both of these solutions, which are well in hand and are sort of understood to be obstructions to this sort of general statement. So what we'd say then at the end is that normalizing, so choosing a particular set of coordinates and really fixing them, so after normalizing by a particular gauge solution, we should at the end decay, through a suitable foliation to some linearized Myers-Perry. So Schwarzschild is not going anywhere except to a Myers-Perry in the evolution. So the gravitational wave is not doing too much besides exactly what we'd expect. In other words, we sort of have a known picture of what the evolution should be at the end. So that's sort of the first piece, just giving some background. But let me talk about the feature of Schwarzschild-Tangherlini that allows or makes this problem tractable. It's just the fact that they have spherical symmetry. So we have this isometry subgroup acting upon it. Of course, they're also static. So we have this time-like killing field as well. So let's see, we can form a quotient as a consequence. And let me just introduce some index notation. So for this quotient space, this sort of TR space, I just want to use capital Latin letters. And for the spherical indices, I want to use sort of lowercase Greek letters. And this sort of distinction will be used later on. We'll split everything according to this this n+2 decomposition. Let me mention also that this quotient space Q and also the orbit spheres would sort of have natural covariant derivative operators that can be extended to the entire space-time, just in the way of, it's a sort of natural way. Okay, so according to this this quotient orbit sphere decomposition, we can just write down the metric perturbation. All it is a sort of a 2 tensor on this fixed Schwarzschild-Tangherlini background. And let's split it according to quotient indices and spherical indices. And sorry, this first line I'm just writing it down in the most general way, and the second line I'm just taking the trace and the traceless part. So this check H is just the traceless piece of this purely spherical 2 tensor, and this H is just the trace piece. Okay, so the useful thing, the fact about spherical symmetry that really kicks in is that we can just regard these as various objects on the orbit spheres, pieces or sections of various sphere bundles. So basically you count the number of Greek indices, and there you have it. There you have what sort of tensor it is. We have the cross terms as covectors, this check H as the symmetric traces 2 tensor. I should have just said 2 tensor. And these other ones as simple functions, scalar functions on the orbit spheres. And there's sort of a decomposition of tensors that sort of carries through. So for a spherical covector, we can split it into sort of a scalar potential piece and also a divergence-free piece. I mean, this is sort of intuitively plausible, or passes the smell test of counting. This divergence-free condition on this p hat is sort of a one-dimensional constraint, and then we fill it in by adding in a scalar potential. For symmetric traceless 2 tensors, there's some more complicated decomposition. So we can write it down as the traceless Hessian of a scalar function, some sort of covector, and then a divergence-free traceless symmetric 2 tensor. So these are just facts about tensors on Sn that are sort of elementary, but the point is we can sort of apply them now to the metric perturbation. So we can decompose the metric perturbation into 3 pieces, like so. Namely, we take the cross term, and we split it into a scalar potential piece and some sort of divergence-free piece. We take, well, we keep the trace part, the traceless piece, this check. On the last side, we can split it into a traceless Hessian piece, a covector piece, and a divergence-free symmetric traceless 2 tensor piece. So it's not obvious where this is going, but okay, let's say for now we can do this decomposition. It might have some use. So the linearized Ricci tensor will also get such a decomposition. It's just a 2 tensor on the background as well. And the sort of notable thing is that actually this decomposition preserves the splitting in the linearized metric. So in other words, when I look at the linearized Einstein equations, when I take delta reach is equal to 0, it turns out that the pieces of H1 are only talking to each other, the pieces of H2 are only talking to each other, and the pieces of H3 are only talking to each other. And it allows me to study each of them separately. So this is just some ghastly expression. Let me just say that this is the cross term for the linearized Ricci tensor. It can be split again into a sort of a scalar potential piece and a covector piece, which is divergence-free. You'll notice that in the sort of expression for this potential piece, these are all, so in the expression for this scalar piece, these are all scalar pieces also of the linearized metric. So this is H, H2, H2H, this cross term, H sub A, and little h sub AB. So yeah, this is just summarizing. I mean, each of the 3 pieces is itself a solution of linearized vacuum Einstein equations. So they're only talking to each other in these equations, and so we can study each of them separately. And the analysis becomes not simple, but much less complicated. So the general approach in sorting this out is that we have this complicated linear system for each of the 3 pieces, H1, H2, H3. We try to determine sort of a decoupled wave equation in line with the sort of nature of these Einstein equations for some gauge invariant master quantity. So I guess it's difficult to find the master quantity, it's difficult to find the decoupled equation, and then having estimated this quantity, using some of these modern techniques I mentioned that have developed in the past 10 years, we would try to use it to pull back the linearized metric. So it's one thing, I guess, to estimate this master quantity. It's another thing to really control the solution itself. Okay, so let me try to get the simplest example. So this 2 tensor portion. So this is consisting of this traceless symmetric 2 tensor, which is divergence free. This H hat. And it itself is actually a gauge invariant quantity, and it itself serves as the master quantity. When we go look at the Einstein equations, what pops out is simply the wave equation, like so. And this is actually quite a nice equation. The analysis of the past 10 years really kicks in. And let me just mention at some high level, so there's sort of a known issue at the event horizon where the sort of natural energy degenerates or breaks down, and this is sort of a problem compared to the standard analysis in the Minkowski space of wave equations. So this redshift multiplier of the Fermi-Raniansky kicks in. Moreover, there's sort of this known trapping effect that happens in Schwarzschild. There's a photon sphere, and so this Marowitz multiplier is also needed. But both these things could be adapted, and dispersion of this H hat is pretty simple to demonstrate.
That happens in all dimensions?
Yeah, there's a simple photon sphere. Moreover, there's a positive surface gravity. So there's some very general sense in which those are the 2 things you need to make all this stuff. Just check all these boxes. And I guess I mentioned at the last point that usually you find a master quantity, and then you sort of need to reconstruct the linearized metric. In this case, it's sort of the simplest possible 3 pieces. There's no need to actually do so because we're already estimating the H hat directly. So this will be in contrast to the covector portion to follow. So in the covector portion, we have these 2 quantities P and Q. I'm not going to write them down there. Well, I guess I will write down Q eventually. So these are at the linearized connection level. They sort of involve derivatives of the metric. So some first-order partial differential operators applied to this linearized metric H2, and they'll satisfy these wave equations like so. And these are much nastier than the wave equation we just considered because we have sort of quadratic growth in a bad way for these potentials Vp and Vq. So as dimension becomes large for dimension n greater than 2, we get negative potentials and we get negative terms contributing to our sort of natural energies and our redshift energy, to speak of it too. So this is quite a difficulty, and it sort of represents something new and sort of an obstruction in the analysis that we're trying to move beyond. So we've sort of sorted that issue out, and let's talk about, so let's just say the analysis for these things has been done, and P and Q are understood. Let me talk a little bit then, having done the analysis for P and Q, how is it that we would actually estimate the linearized metric using the estimates on P and Q? So given to some sort of covector, let's say it consists of just a spherical piece that is divergence-free, the gauge transformation, so transforming by some associated infinitesimal change in coordinates, changes H2 like so, changes each of the components like so. So this master quantity that I just described as satisfying some wave equation, this master quantity is actually defined like so. And we can actually see manifestly that it's gauge invariant. So the effect of a gauge transformation would be to insert one of these, take its symmetrized gradient, but this is sort of offset exactly by what happens when we change the gauge of this with a single Greek index. So Q is a gauge invariant quantity, and let's actually choose our x. Let's actually impose some gauge. So we choose some sort of gauge normalized solution, and we choose this x specifically to kill off this h hats of alpha. So what we've done is we've just left cross terms. So in terms of this h2 prime, this gauge normalized solution, the master quantity just looks like so. So it just looks like some sort of spherical derivatives of these cross terms. In that case, so we have estimates on Q already from the analysis of this wave equation it satisfies. We can simply sort of pull back the linearized, these linearized cross terms in a very simple way just by using elliptic estimates on the sphere. So in that way, I mean, it's less direct, I guess, than the two tensor portions. So we had estimates on P and Q, but we need to sort of go backwards to get the linearized metric as well. By the way, I mean, that whole thing is sort of a cartoon. I mean, you actually do need P to come in some sense, and it's a little bit more complicated than that, but that gives you some flavor of what's going on. Okay, so the scalar portion is just so horrendously complicated, I won't even get into it. We need to decompose into spherical harmonics. Let's say we have harmonic number L. Of course, these things can be generalized to higher dimensional spheres. And we'll have some sort of harmonic dependent wave equation with some harmonic dependent and also independent potential. And this thing would just take up a whole slide to write down this V sub Ln, so it's really pretty rough. The potential is, again, very, very nasty. It's negative in the way that the potentials for P and Q are, and so again we have sort of an obstruction. Actually, in terms of getting around it, at this stage we sort of understand for a very, very small dimension, of course for n is equal to 2 and a little bit beyond, and also for very large dimension, but we don't actually have the complete picture. And let me just say that supposing we had such a picture, then we need to reconstruct the linearized metric. The way to do that, it seems to be, it's sort of a straightforward application of our earlier contribution of sort of using some modified Chandrasekhar gauge. This is sort of a gauge normalization that Chandrasekhar has in his book on black holes. It needs a little bit of massaging, but it can be used to sort of pull back and estimate the linearized metric using this master quantity Q sub L. So in that case, we have, I guess, all three of the pieces, H1, H2, H3. We have these master quantities, we estimate them, we pull back the linearized metric, and I guess that's really the whole story. Okay. Am I way over or way under? I have no sense.
You're into questions.
Oh, whoops, okay. Okay. Okay, sorry about that.
Yeah, so questions for Jordan.
I'm trying to understand this whole linearized approach. So let's take the scalar problem, for instance.
Okay.
So you've done your spherical harmonics decomposition.
Okay.
would I be right to think that each L is an independent problem?
Yeah.
So they don't talk to each other, right?
Yeah.
And these L's must be pretty damn similar to the e to the I omega t L's that the modal analysis would have given. How would this be different?
It's not, no, I mean, each of the L's would and so I guess the L is about decomposing along the spherical harmonics.
Yes.
The e to the I omega t is imposing a particular type of dispersion, and the problem really fundamentally is
But
about.
there also, they would then break it up into L's and M's and solve the problem, I presume.
Yeah,
But the time dependence is not omega t.
But you, I don't know, it's closely related to what you're saying. I mean, can't you just Fourier transform something with time dependence 1 over t?
right. And then if you think about the associated wave equation, you could do some sort of estimates on it. Then you need to take an inverse Fourier transform, but you've got horrible coefficients involved, like in the actual D'Alembert operator. It just feels like it would be quite nasty. There's a whole school of thought that does this sort.
So for each one of these modes right here, each one of these master quantities, I could introduce a Fourier transform, and I could introduce a spherical harmonic transform too, and get some eigenequations, right? Some radial wave equation I have to solve for each mode.
Right. This is the old approach.
Right. So if I did that, I should still be able to get, in principle, what you're talking about, this 1 over t time dependence when I Fourier transform back to real time.
Right, but then you have to do the Fourier inversion. I mean, it just feels like that's a very formidable type of thing. I think there's like a whole, like these sort of Melrosian techniques with the school of thought using.
So at the end of the day, the frequencies you would get for that process, each one of them would be exponentially decaying.
Yes.
But when you add them all up, you'll get the 1 over t. That's what you're
Yeah,
saying?
something like that. Yeah.
Okay.
Although I mean, I wouldn't want to be the one to add them up.
Well, you can have a computer.
This can be done numerically also.
Yeah. No, I mean, again, the picture that physicists had, by the way, it's very, very accurate to life, I guess. There's not that, it's a very pedantic type of thing that we're doing here. I think it's safe to say.
Yeah, but I would say, so let's say I did the exponential analysis, and I showed that every single mode that I can analyze is a decaying or a neutral mode. There's no growing mode. Can you imagine then a situation where, let us say, I get that result for all of my linear modes? Can you imagine a situation where that same problem, when you hit it with your heavy-duty analysis, suddenly becomes unstable? Could it?
Yeah.
That's where I'm getting a little lost. I can see that you get the 1 over t, and it's a lot more complicated to sum up exponentials and get a 1 over t. Okay, that I can understand, but it's still a decaying solution. Could that problem? I mean, I'm not talking about this specific problem, but in general,
Right.
could the problem actually end up being unstable, even though all the modes said that they're stable?
I can't think of a particular example actually. Although I mean, yeah, of course, it is the case that this mode solution is strictly weaker than what we're doing. But then, yeah, I mean, the question of whether there's some distance between them, I'm not sure. I don't actually know of any example where the mode stability is the case, but then this
analysis actually says
no,
it's
it's true.
That would be a fantastic thing. Yeah, then you can say, look, guys, you really need to listen to me.
I think the mode stability is serious stuff too. So.
Okay, well, I think in the interest of time, we should move on. Let's just thank So our next speaker today is Chi-Kwan Chan. So CK is currently a visiting fellow at the BHI, so he's here and sitting, and you should feel free to find him out and start up conversations also. CK got his PhD from the University of Arizona, and he was a fellow at the Institute for Theory and Computation down the road at Harvard, the CFA, and he's an expert in computational astrophysics, and today he'll be telling us some code that he's developed for ray tracing.
Thanks for the introduction, Michael. So this work was done together with Ferrier and Dimitrius. They were always sitting here last year, so I guess many of you actually know them much better than me. So when I was preparing this talk, I looked up the list of talks from last year, and I'm super impressed by the diversity of the talks. And I guess that's the special thing about the BHI. We have different people from all different angles studying black hole related stuff. And that's the reason, instead of jumping to this really specialized ray tracing thing, I decided to put it to be more introduction, so that people with mathematical, philosophy, and physics background will appreciate a little bit of what the astronomers are doing. So, so let me start with this classic example of black hole accretion physics. So the system we are considering is called X-ray binary. So we have a stellar mass black hole that's orbiting with a secondary star. So two objects that are orbiting around with each other. The secondary star, because of the gravitational pull from the black hole, the matter starts to stream around. And because of conservation of angular momentum, they cannot just fall onto the black hole. Instead, they form this accretion disk. And somehow, eventually, they peak out and create radiation, create gas, and all the interesting astrophysics phenomena. And if you do some order of magnitude estimate, this is really interesting because it's the most energetic phenomenon in the universe. It's actually more efficient than nuclear fusion. That's the So we often say the black hole, they are the most energetic objects in the universe. Now, this black hole, they are stellar mass, so they are few solar mass. And in the other extreme, we have black holes that are a few million to billion solar mass. So these are supermassive black holes. We believe they exist in almost all galaxies. And if we look at the structure of the galaxy, so this axis is dispersion of star inside galaxy. When we compare that with the mass of the central black hole, we see this kind of correlation. So this suggests that although the supermassive black hole is a tiny thing, within the galaxy, they actually have something to do with the evolution of galaxy. And this is an active area of research in galaxy formation. And of course, our Milky Way is a galaxy, so we expect to see a black hole at its center. This is actually an image of a movie of our galactic center taken by adaptive optics. So it starts in 1993, I guess. People take the image and then they follow these stars, and these stars actually orbit around this radio source. And by just simple Newtonian gravity, we can figure out there are few million solar mass in this really tiny area.
What are those little green lines?
Which green line?
Star.
The names of the stars.
Yeah.
Yes.
So so this brings us to this really interesting project led by Shep here. So the Event Horizon Telescope is trying to resolve the event horizon of Sagittarius star, and at that point we will finally be able to tell Sagittarius star is a black hole. Okay, so I told you that black holes are the most energetic objects in the universe, but what is the physical mechanism behind that? So let me spend a few slides on that. So this is a really simple sketch. The x-axis here is the distance from the black hole. So that's the event horizon. That's the innermost stable orbit. If I bring a fluid element really far away from infinity, I put it to the black hole, then these are the available energy of that fluid element. And eventually, this fluid element will orbit around the black hole, will heat up. So we got some thermal energy in the budget, and it will start to grow and radiate. So that's the radiation energy. And now we can fill out your different physical mechanism between this energy and ask you how this happened. So just based on basic fluid dynamics, we will say maybe the viscosity is enough to turn the kinetic energy to thermal energy. However, if you look at the actual number, it's not going to do that. Although black holes, they are small, but they are still astrophysical, or the viscosity is not strong enough to make this happen. So in order to save this your whole physical picture, we need to go back to basic fluid dynamics. So I highly recommend this book. So what I did is I scanned many pictures from this book and I put it here. So this is actual image of physical experiment, not numerical experiment. We start with some fluid on the left, we put a cylinder here, and we trace out how the flow moves. So when the Reynolds number is small, Reynolds number is proportional to the velocity of the fluid in the scale, and it's inversely proportional to the viscosity. So when the velocity is small, viscosity is important, the flow is pretty much laminar. It's just like that. If we increase the velocity or increase the Reynolds number, then we start to see this interesting fluid dynamics phenomena. This is called separation. We start to see these vortex. And when we increase the Reynolds number further, then the instability start to develop. This is called the non-counting vortex. And if we, well, actually, I have a really interesting movie here. So this is a satellite image over the ocean. There's an island here. And when wind come by, you can see this, your one-counting vortex start to form based on the cloud. So this thing is really happening in nature. And when we increase the Reynolds number further, these vortex start to break down. The large-scale motion cascade to this really small-scale motion. And that's how we can transfer large-scale kinetic energy to thermal energy. Okay. I actually went really fast, so I think I have some time to show you these hidden slides here. So you know when? So this appeared in explicitly a few days ago. So when I was doing this turbulent work, I always train you quantum mechanics, general relativity. They're super exciting. And when I'm doing turbulence, I think this is boring, and not exciting. But I guess my slides is trying to convince you that in order to do the interesting GR work, we actually need some fluid dynamics. Okay. Okay. So this is your output story. And so is it going to work in the accretion disk? So we can do a numerical experiment. The setup is like this. We start with astrophysics. We set up the coordinate, and we imagine ourselves co-moving with the fluid inside this disk. So in the local coordinate, we have set up like this. And it turns out that this thing is unstable. So this is a simulation I did a few years back. The green stuff here, they are the Y component of the magnetic field. Initially, they're really small. They're just tiny magnetic field fluctuating around. But when we let the simulation run, this thing becomes unstable, and you start to see this channel solution develop. So these are all magnetic field. They're initially really small, but because of the differential rotation, they grow. And after this spinning finish, you will see the channel solution eventually face a secondary instability and break into this turbulence state. So just a tiny bit of magnetic field in your accretion disk then is able to drive instability and drive turbulence. So the whole story now complete. Okay, so we can put in turbulence energy here. So kinetic energy, because of this nonlinear cascade of turbulent energy, and turbulent energy by viscosity, resistivity, we get thermal energy, and then we get radiation and other interesting things. If you actually look at the energy budget, the turbulence energy is quite small compared to all the other, but they are the interface that allow this transfer of energy, and they are really important. Okay, so I just finished my introduction. I told you the story how this happened, and now we can finally go to the radial transfer part, which is the main topic of this talk. Okay, so let me first show you a visualization. That's not the thing I want. So this is a visualization of a black hole accretion disk. Let me start again. This simulation was done by Ramesh's group. And here I use a density threshold that you can see the middle part of the accretion disk. This is what I told you. And because this is a model for Cedric star, the simulation is actually quite fake. this is the actual solution, full solution. And what you're looking at is the density. So this part, this empty part, is called the funnel of the equation disk. And I can turn this rendering to visualize the magnetic field. So now I'm plotting the plasma data. The bright part there, the strong magnetic region. So the funnel is pretty empty in terms of density, but there's a lot of magnetic field around. And I told you about all of this turbulent MHD story. So you can see this complicated structure of magnetic field here. Okay, so now let's go to radiative transfer. So in Arizona, we developed this numerical algorithm called X-ray. So what it does is it follows no geodesics in curved space-time. So this is not something new. It's a standard numerical algorithm. But the interesting thing we did was we used this latest technology called the graphic processing unit. So they are computer hardware designed to do computer vision and video games. They are really good in doing number crunching stuff, and they are much faster than the CPU. So we wrote a code, we make it run on the GPU, and they are about 30 times faster than typical numerical, typical algorithm using similar methods. And we use this code on our GPU cluster in Arizona, and then we start to generate a lot of image of black holes. So I can show you another demo here. So this is the GUI code actually running in real time on my laptop. So I start with 250,000 photons. So they start far away from the black hole, and then I send them to the black hole, and because of the curved space-time, they got deflected, and they got banged.
So this is running in real time?
This is running in real time.
On the GPU on your laptop?
Yes, exactly. So this is not a movie, it's running right now.
Okay.
Yeah.
How many rays?
Quarter million photons. Yes. And some of these photons will got stuck on the black hole. So if I run this simulation backward, then you can see the shadow of the black hole. Okay. So, but this is only done on my laptop. I turn on my laptop. So when we do this with the GPU cluster we have in Arizona, then we start to create this really nice simulation of ZJ star. So this is a simulation showing you different wavelengths. We start with, let's see, long wavelength, and you can see the body of the accretion disk is blocking the event horizon. But as we go to higher frequency, longer wavelength, then we start to see the shorter wavelength, and we start to see the shadow of the black hole. And this is one of the reasons why we use 1.3 millimeter for the event horizon telescope.
But so those are jets we're seeing.
Mm-hmm.
But in observations of Sagittarius star, we don't see jets yet.
It's a great question.
So this is a particular fitting to the data we already have. Okay, so there are a couple of things there. So first, this is in log scale. So you really bring up the jet. If we look at it in linear scale, the jet is less. It won't show up like this. So on the other hand, we have many parameters that we can fit to in the radiative transfer equation. So this is just one of the fittings.
There's also no scattering. And the
Okay.
jet proponents would say, oh, it does look like that, we just can't see because.
Yeah, it's also possible.
But there is no evidence for a jet. That's, it's what Peter is saying is true, right? The data doesn't show evidence. Forget
But
about
equally well, it's true to say there is no evidence against jets.
Well, there's no evidence.
Because of scattering.
Is there evidence against tooth fairy?
Yes.
I think so, yeah, I think so. I'm satisfied. I think tooth fairy is what exists.
Is the direction of that, is that direction of that jet, is this thing spinning in the middle?
So this is only a static image, but the next one I have a movie. So this thing is now.
No, but is the black hole spinning?
Yes,
Yeah.
this is a spinning black hole. It's spin 0.9, I believe.
And are the jets aligned with the spin?
So it's actually a really interesting question. So for this simulation, it's aligned with the jet, but depending on the inclination angle, you can see the photon emission around.
Wait, I'm good. Okay, so there's no little arrow on there that tells me which way we're not seeing the black hole itself, right? There's no arrow that tells me which way it's spinning. So
Yeah. So
now it's spinning up.
So the spinning axis is here.
Yeah.
But I'm turning the camera in this direction.
Okay, so why? So the stuff seems to kind of boil off around the equator, and then what makes it go up? It doesn't shoot up.
So that's the work of Ramesh.
It's following magnetic lines or something?
Yeah, pretty much. I guess the story is.
The magnetic lines are doing this?
You're doing that,
Yeah.
and you are spinning them because of dragging of frames,
Yeah.
and that gives you outflowing gas, energy, etc.
But of course, we don't know that the black hole is Sagittarius star has
Who
spin.
knows? Yeah.
Yeah.
Right. This is a one particular
This is a spin of 1,
It's
the
0.9.
maximum 0.9.
Yeah.
So of course, if you dial down the spin, then there would be less of a jet in the future. And so that's the issue, whether the Sagittarius star has a spin.
So there's a magnetic field here in this picture somewhere, right?
Yeah.
And would that magnetic field, would those lines be not all knotted up on the axis of the spin?
So the
Lines were helical, yeah.
They do that.
So there'd be almost a singularity in the middle of that jet and the magnetic field, is that right?
Yeah, except there'll be very little field there. It'll be kind of almost a straight line here, and then it becomes more and more helical as you go out.
They'll spread out, you're saying?
It's not, I mean, there's nothing non-analytic at the center.
There's nothing non-analytic.
Yeah.
That's right. So they're basically following the magnetic field lines? They're not, that's what we're seeing? Or do they kind of
See,
spin
this
off?
is showing radiation.
Right,
To get the radiation, you need both gas and magnetic field.
right.
And like CK said earlier, if you look at just the gas, there's kind of an empty region in the middle. That's the
Yeah.
funnel.
Yeah.
If you look at the magnetic field, actually there's a lot of magnetic field in the funnel, but there's very little gas there. And so the radiation tends to be concentrated in the interface between these two, along the wall of the funnel.
so this is the magnetic field, and this is the gas.
Right. So gas is kind of empty there. The magnetic field is mostly there, and where the two meet tends to be the place where you see the radiation.
What is the prescription? A synchrotron version? Or?
Synchrotron is what I think.
Yeah, the synchrotron is
So
dominating.
you make some assumptions about the relativistic population of
No,
electrons.
it's thermal.
Oh, this is thermal.
Thermal synchrotron.
What happens if you put the spin up to 1? Does it look very different, or is that not something
It
you
makes
can
the
do?
computer unhappy.
Well, suppose you put it to 0.99, does it look very different, or?
It becomes more powerful, the jet.
Is that 0.99 now? You just did it.
No, this is 0.9.
I think.
Yeah, so this is again a simulation done by Ramesh. So this your GRMHD simulation, they are really expensive and difficult to do.
I think we have gone up to 0.98, but there are some people who have done
Is
even
it-
higher.
Does it look very different, or does it get skinnier? And
I think it just becomes more powerful, the jet. But nothing diverges as far as I know.
is there an analytic formula for that angle?
Which end?
The opening angle?
The opening angle.
So what is 80%?
It's, I mean, it's not a single cone, right? It's
Yeah.
parabolic, but not perfectly parabolic. It goes to some power, different from 2.
Is it guided by the hydrodynamics, the kind of opening angle of the disk itself confines the
Yes.
magnetic field? So that
Yes, it is a competition between the magnetic field, which wants to open out, and the rest of the disk, which says, no, don't come here. So, yeah, that competition finally self-consistently gives you a shape. which becomes more and more collimated as you go further out.
There used to be these solutions to Polish donuts, but this is different.
No, this is, yeah. Those didn't have fields, and
That's right.
yeah.
Maybe you could estimate it with 1D hydro energy.
There's something I can't quite tell from that picture. Is that jet, is it all coming from one fixed polar angle, or is it coming all the way up to the top?
So I actually don't understand the question.
That you've got this yellow stuff
Mhm.
coming off the spinning black hole.
Mhm.
Is it coming off everywhere, or just from some fixed polar angle?
This is the radiation. Ramesh mentioned that most of the radiation comes at the interface of the jet at the disk and magnetic field region. So maybe what we're seeing there is that interface, is that yellow edge of that.
So it's a special angle.
Just because of, how the
I mean, it looks like there's nothing coming just above and below the equator. I can't tell as clearly if there's stuff coming from up near the North and South Pole.
there is power coming out there, but it doesn't reflect in the radiation that we are seeing.
So I sketch a picture here. The plan is not that good, so it's not that helpful. So that's the black hole. That's the body of the accretion disk, and these are the strong magnetic field. And because the radiation is proportional to your density in the field, so there's some boundary here, the funnel wall, that you hit the maximum radiation. That's the main thing we are seeing. Now, however, if you're talking about this ring here, is the photon ring. So this part, this radiation actually come from everywhere. They got the
I don't think that's what Andy is. Andy is asking, there seems to be one latitude from which stuff is coming out. And
Right.
you wanted to know whether there's anything going on at other latitudes, right?
There is a critical latitude at which d by dt goes from being time-like to being space-like
On the horizon.
on the horizon. Is it that?
So I don't think that's the case. I think it's just the sweet spot for the radiation. So if you look at a different frequency, I think that will change.
It's the shape of the ergosphere.
Is the spectrum, the emitted spectrum from Sagittarius star
That's a
or
different
is
thing.
it expected to be
This is,
relativistic?
the ergosphere is,
So we have a
Right.
a lot of this is inside the ergosphere.
That's what this is supposed to be.
That's the red channel. Okay, so I guess we have a lot of great discussion. So this is what happened when I show this movie. We always get great discussion. Okay, so
Andrew can give you more current, richer simulations. You can make even better movies.
yeah, sure. We should.
He can even put non-thermal particles for you, but maybe in a couple of months, yeah.
Okay, yeah. So stay tuned for that.
Yeah.
So yeah, this is all about the first version of GUA. As I told you, it used some pretty standard numerical algorithm. So one standard thing I want to say is it's based on the Boyle-Nyquist coordinate. So there's a coordinate singularity along the pole, and it just gives you numerical difficulty when you have a ray hitting the singularity. So I won't go into the detail of this, but in the second version, one major improvement is now we switch to the Cartesian Schwarzschild coordinate. So there's no coordinate singularity in the equations anymore, and it just makes things better. Now, however, the Schwarzschild coordinate, if you look at the metric, there's no zero in the metric. So it looks like this is more complicated, and you will slow down your algorithm. So one major achievement we have in this second version of the code is we look at the equation and then we start to manipulate them. So the first thing we realize is when you do ray tracing and you do it on the computer, you actually don't need the Christoffel symbol. It's better to just expand the Christoffel symbol out. Then these two terms here, they're here to symmetrize the Christoffel symbol for two of the indices. But now we can just put them together because this part is also symmetric. So there's no point to do that manually. And once we do this, we can change the index by the magic. And now the most complicated term in the equation, now they look identical. So this is just the derivative of the magic. And we can pull this out from the equation. Pull this out from the equation. So this is, so far it's completely generic, it's just the geodesic equation. I haven't even specified the magic. But this is telling us that when we want to solve this problem numerically, it's better to deal with this form of the equation. And an even nicer thing is now we can plug in the Cartesian spatial coordinate, and the equations simplify further. So the Minkowski measure, they're just one, so the computation is trivial. So they're just pulling different columns and rows of your magic. And this big complicated thing here that demands most of the computation is actually a single scalar that you can pull out for each view. So this simplify the computation a lot, and we implement this, and then we find out this code is as fast as the original code, even though the computation
What do you
is
mean computed once for all mu? What does it mean?
So there are 4 equations here, right? And mu is here.
Yeah.
But this thing is
So
just
that guy doesn't involve mu. That's what you mean. Okay.
yes.
Okay.
Yeah, so is that you simplify the computation a lot. Okay, so
But these equations, of course, are 4 conserved quantities and they've been integrated. That doesn't somehow isn't helpful.
So I guess that's the thing about your numerical method. This conserved quantity, they are good for doing things analytically. But in terms of the computer, in this form, because you don't need to handle sine and cosine, because the trick we put in here is actually faster to do it this way. Yeah, it's a little bit counterintuitive, but that's the trick we figure out. So this is a new method. So we decide to put it under some serious numerical test. The test we have is this unstable spherical photon orbit. So this is for this orbit, there's some parameter that the geodesic will go through exactly the pole. So we just zoom into that region, and then there's no problem for the numerical method. There's no coordinate singularity, so the geodesic just go through the pole without any problem. And this is just a simple convergence study plot. It's just showing that when we use a smaller time step, and the error in the calculations goes down. So it converge, as expected. And this is another test. So the one nice thing about this is it doesn't assume photon or particle. The same algorithm without any modification works for both photon and matter particle. So we use this same algorithm to do particle orbits, and you also show agreement with analytical result. So
So CK,
yes.
you are evolving the geodesic equation, right?
Yes.
And your 4 velocity is changing.
Mm-hmm.
How do you ensure that the norm of the 4 velocity is whatever, 0 or -1, as the case may be? Is that an extra condition, or is one of your equations guaranteeing it?
So
You can have to conjure if you're not using the conserved quantities, right? So
That is analytically.
So it
But
should
does
be
the computer know about that?
It shouldn't, right? It should be able to test whether it's conserved.
That
or
should
not.
be a way of
Yeah,
telling
there should be
whether-
a test.
Yeah.
so
This is what you're testing here.
yes.
Okay.
Yes. So there are different versions of the algorithm that you can choose from. So some of them use that as a constraint, but if you use that as a constraint, then you cannot pass it.
Okay.
So for this plot, I'm just saying, okay, I have the equation, I'm just evolving that without worry about that conserved quantity. But as this plot show, when we make the steps smaller, it go down to machine accuracy. That was 10 to the minus 30.
And x to the -4 convergence is because you're using Runge-Kutta 4,
Yes, it's a 4
4th order method. Okay.
Yeah, So I guess Michael stands up. That means I'm running out.
And he's a tall guy.
He has no weapon.
Yeah. So again, I told you that your algorithm is really fast. So this is just a benchmark of this algorithm. The new version is partial coordinate. The old version is the Void-Lucas coordinate. I'm just running it on different CPU and GPU. Just compare the result, and you can tell the new algorithm, although it looks more complicated, is actually faster.
Are all those GPUs, or there's some of them are being?
So let's see. So these are GPUs, and these two are the CPUs. I think this is the CPU on my laptop, and that's the CPU on the supercomputer in Arizona.
Sorry, what's the number?
Bigger
or smaller is better.
So this, okay, so I forgot to say that. This is unit of nanosecond.
Okay.
So it takes 2 nanoseconds to integrate 1 geodesic.
Okay.
Okay.
Smaller is better.
Okay.
Yeah, smaller is better. And
Size matters.
I will just put on my summary here.
Okay, questions for CK?
So, CK, the point is not that it is faster.
Mm-hmm.
It's much better at handling the pole.
Yes.
I mean, that's the reason why you did this, right?
Mm-hmm, yes.
The old method, you could actually see problems with it.
So we have
Near
a
the
trick.
axis.
We have a trick to avoid that, but it's kind of ugly, and we don't want to do that.
You didn't want to do that.
And also, so the trick works when you're using an inclination, say 30 degrees. So sometimes we have problem. We have a method to go over that. But if we're going to 0 inclination, then the old method won't work at all.
And the new guy doesn't care,
Mm-hmm.
whichever way.
So there's not much of a jet, well, or at least not a very bright one from say J-star, but there is from M87, and we're presumably kind of looking down the barrel of it. Can we figure out what the spin of M87 is from the shape of that?
That's
Are we going to have enough resolution to?
That's the EHT goal, and there were some constraints already put from previous data, and Shep can comment on the spin. Shep, what are the limits on the spin right now on M87?
Well, they're just some guesses right now. We fit some sizes to the shape, and we fit
The
it
shape
actually,
of what?
Well, we fit some sizes to the emission region, and we equated that to the innermost stable circular orbit, which is a bit of a hand-wavy argument. When you do that, you get the size of the ISCO, and that is very sensitive to spin. The shape of the shadow, though, is not very sensitive to spin. The actual
but
silhouette
this is something
itself.
else, right? It's the shape of the jet, which is the most visible thing that you see, right?
Yeah, the jet shape, Ramesh is also an expert here. It depends a lot on the surrounding medium,
The jet is far out.
the launching.
The inner part.
The EHT is
Well,
going
that
to
was why I was asking whether the shape of that was sensitive to the spin.
Oh, the base of the jet.
Where the collimation
Why
goes up.
does it? What fixes that angle at all? It looks like it wouldn't. It looks like it would flatten out with the spin, with no spin, and looks like it might get very narrow with high spin. And so, that shape of that, has a question been asked how that behaves with spin?
I think the differences come close to the black hole. Because, the material
Close to the black hole.
Yeah, I think far out.
But what sets that angle? You're saying that angle is there's a universal angle that doesn't depend on
I
the spin?
wouldn't say it's universal. It probably depends. For the same spin, you could probably get somewhat different angles in different systems. Because at the end of the day, it's a competition between this gas is fighting to get in,
Yeah.
and some of it is getting pushed out, and there's this magnetic field sitting there.
Yeah.
And
We're also going to see the shape of the jet, the shape of that jet close in. We are going to see that, right? Aren't we?
Yeah, the opening angle, the base of it. Yeah.
Yeah. So couldn't the opening angle depend strongly on the spin?
right next to the black hole, you mean?
Yeah.
Yes.
Conceivably.
Yeah, but even that
I
might be
think the
determined.
amount of
I'd like to see this picture run 3 times at spin 0.6, spin 0.9, and spin 0.99.
Your wish is our command. Andrew, Andy has a shopping list.
Okay, so I think in the interest of time, we should continue discussions, after people disperse. But thanks all for coming, and again, both speakers today are locals, so reach out if you have ideas.
There is a pizza at 4:30.
And there's pizza with the speakers at 4:30.